Hey folks, it's Mr. Ray here with our next lesson in grade 12 vectors. We're working in the unit regarding equations of lines and planes. The last three lessons we've looked at equations of lines. First in R2, we looked at the vector parametric and symmetric equations in R2, and then we looked at basically the same thing in R3. We also looked for R2, we had something called the Cartesian equation, which was exactly the same as the standard linear equation that we did in grade 9. We just created it from a vector perspective. So we finished with equations of lines, and now we're going to move on to equations of planes. So we're going to have two lessons on equations of planes. This first lesson here, we're going to be looking at vector and parametric equations. So based on our lessons on equations of lines, we know what the vector and parametric equations look like, and we're just going to extend them to planes. So before we get into the key concepts, I want to look at this, this little diagram from the textbook. Hopefully it focuses a bit better. There we go. Okay. So we've got this kind of blue three-dimensional, well, it's a parallelogram in 3D. It's the way we represent planes in pictures, which our pictures are obviously in R2 because they're on a piece of paper. We represent them with basically a rectangle, or in this case a parallelogram. So the blue parallelogram here is the plane that we'd like to create an equation for. So the way we're going to do it with vectors is very similar to the way we did it with lines. So if you remember, we had this vector we called R0, which was a position vector that went to any point that's on the plane. So basically you start at the origin, you go to any point on the plane, and you've got your position vector. Okay, once you're at that point P0 on the plane, in order to go to any other point on the plane, well, now that this is also two dimensions, we need scalar multiples of two vectors that define the plane. Now, those two vectors could be any vectors along that plane, as long as they're not collinear, which is as long as they're not scalar multiples. So you can very faintly see this kind of yellow, I think it's just faded here, yellow vector and the green vector. Those two vectors, I believe they're A and B, basically define that plane. But in order to define the plane, you have to have basically kind of an anchor point that gets you to that plane. And then once you've got to that point, you can use scalar multiples. Any combination of scalar multiples of those two direction vectors will get you anywhere else on the plane. Okay, so with that being said, let's go back out here. Okay. All right, so I guess we already know what a plane is, but there's something new here, so let's read it. A plane is a flat, two-dimensional surface that extends infinitely far. To represent a small part of the plane, we usually draw a parallelogram, and we use the Greek symbol pi. Okay, so in the previous lessons, when we talked about representing different lines, we just used capital L with a subscript, L1, L2, were lines 1 and line 2. Today, when we have different planes, we're going to represent them with the letter, the symbol pi. So if you had two planes, we could call them pi 1 and pi 2. It's just a math convention, and it is in the textbook, so it's important to know where that comes from. It's nothing to do with, you know, the area or the circumference of a circle. It's just a letter that's used to represent a plane. Just like theta represents angles. It's just a math convention. Okay, so when you see the symbol pi, you know it's just a certain plane that we're talking about. Okay, so key concepts. Let's talk about these equations now. So in R3, if you have this vector R0, which is determined by a point on a line, and I guess this should be plane actually, point on a plane. And you have these two direction vectors, A and B are direction vectors. Then the vector equation of the plane is R, vector R, and that's similar to what we had with vector equations of lines, equals R naught, which is also the same as what we use for lines. But now we have, instead of just one scalar multiple of a vector, we have two different scalar multiples of two different vectors. So SA plus TB. So your S and your T are real numbers, and they can be zero too. Any combination of those scalar multiples of those two vectors will get you to any other point on the plane. Okay, so that's how you move around on the plane, and that vector R naught is how you get to the plane. So that R naught could be any position vector to any point on the plane, and vectors A and B can be any direction vectors that are on the plane that are not collinear. Okay, so if we break that out into components, we've got x, y, z vector is equal to x naught, y naught, z naught, and that's the position vector. That's basically the coordinates of the point on the plane that we know about. And then we have our two direction vectors. First direction vector is A with its components A1, A2, A3. Second direction vector is B1, B2, B3. Those two vectors cannot be scalar multiples of each other, or you won't actually be defining a plane. You'd only be defining a line. And then you have your S and T, which are your scalars. Okay, so really you're just adding on this extra part to the vector equation that will get you basically defining a plane instead of a line. If you just stopped up to that point, that would be the equation of a line in R3. You add this second direction vector, you're now defining a plane. Okay, and then when you break apart the vector equation into parametric equations, same as before. With R3, you've got x equals is your first equation, so it's x naught plus SA1 plus TB1. So it's a little more complicated now because you've got your second scalar multiple of that second direction vector, and the y and the z parametric equations follow the same thing. Okay. Now this is important. There are no symmetric equations of the plane. That's just because it's with the other with lines you only had one scalar multiple, so you could isolate for that. With planes you've got, in this case, S and T, so you can't really isolate for S because you've got that second scalar in its way. Replacing the parameters in the vector and parametric equations of a plane with numbers generates points on the plane. We're actually going to be doing that. So based on the, if we gave a vector equation or parametric equations, we could actually come up with other points that are on the plane. Because there are an infinite number of real numbers that can be used for S and T, there are an infinite number of points that lie on a plane, just like there was an infinite number of points that were on the lines that we defined previously. Okay, so we've kind of ramped up our vector equation to have a second direction vector with a second scalar that gives us, we're basically defining a two-dimensional thing, the plane, instead of a one-dimensional line. Okay, these are the different cases. Let me zoom in a bit. These are the different cases of, given a certain amount of information, how could we define a plane? And we're going to be doing all four of these. So you could be given a line that's on the plane and a point that's not on the line. And that's enough to define a unique plane. Second case, you had two lines that intersect. That will be enough to define that plane that both of those lines are on. If you have three non-collinear points, so non-collinear in this situation means they don't form a straight line, because if they did, then you'd be kind of defining a line in R3. So 3 non-collinear points. And the last case would be 2 parallel lines on the plane, but they're not the same lines. So this word non-coincident means they're not the same lines, 2 different lines. Okay, if they're coincident lines, they're the same line. Okay, and we already looked at this diagram when we were talking about how do we make our vector and parametric equations. So let's move on, try a few things out. Okay, so sorry about that. You'll be seeing, we're going to be going through each of those 4 cases that we saw on the first page where different types of information are given. So for the first one, it says, for each of the following situations, create an equation of the plane. The plane determined by the 2 intersecting lines. So remember that is actually case B. Okay, so how do we do this? Well, the first thing we have to do is find the actual point where they meet. And once we've got that, there's not much work to do. Now, unfortunately, finding that point of intersection is a bit of work. Okay, on this whole page, this will be the most complicated thing we'll do. So the first step is to find the point of intersection of line 1 and line 2, L1, L2. Okay, so what we do is I'm going to do the parametric equations for line 1 and line 2. Might need a bit more room, maybe not. So since these are lines, you may notice that there's no second direction vector. That's because these are lines. And you can tell by the capital L. So lines only have one direction vector, not 2 like planes do. So if I was breaking apart line 1 into its component parametric equations, I'd have x equals 1 plus 2t, y equals 2 plus 3t, and z equals 3 plus 4t. And then I do the exact same process for line 2. So the x parametric equation is 2 plus s. Notice we have different scalars. This is important because these don't necessarily have to be the same, and they probably aren't. So don't make them both the same letter, or this first step isn't going to work. The y would be equal to 4 plus 2s, and the z is equal to negative 1 minus 4s. Okay, so what we're going to do is actually figure out what the values of s and t are that actually make these x, y, z's the same, because that would be the point that they both share in common. Okay, so what we can do is I've got equations for x for the 2 lines, so I'm going to actually set those equal to each other. So I've got 1 plus 2t from here for the x is equal to 2 plus s. I don't know why I put a plus there. Equals 2 plus s. And if I take away the 1, I've got 2t equals 1 plus s. Actually, yeah, I'm trying to get s by itself. So what I'm going to do is I'm going to subtract 2 from both sides. So 2t minus 1 is equal to s. And we'll leave it there for now. So I basically got an equation that isolates s in terms of t. So I'm going to do the second equation for y. I've got 2 plus 3t is equal to 4 plus 2s. Okay, so I've got, what am I going to do here? I'm going to subtract the 4 from both sides, so I get negative 2 plus 3t equals 2s. And I'm now going to replace my equation that represents s in terms of t. I'm going to plug that in here. So I'm going to have negative 2 plus 3t is equal to 2 times s, but I know s is equal to 2t minus 1. And now you can see I've got, basically this is, linear system solving by substitution. So I'm going to solve for t. So I'm going to get negative 2 plus 3t is equal to 4t minus 2. And if I subtract 3t on both sides, I get a t over here. And if I add 2 to both sides, I get a 0 over here. So if I'm solving this linear system so far, I know that t equals 0. And now I'm going to use this here. So s is going to be equal to 2 times t, which we know is 0, minus 1. So s is equal to minus 1. So let me switch this around so it reads a bit better. I'll just put t equals 0 instead of 0 equals t. Okay, so we got values for s and t that work for the x and y parametric equations, but we're not quite done yet. We got to check and make sure they also work for z. Okay, so I'll make my third equation. And here I'm just checking for z. So I've got, if I go back to these equations for the z, 3 plus 4t, let's do it this way, 3 plus 4t is equal to negative 1 minus 4s. And if I plug in my t equals 0, I get 3 plus 4 times 0. And if I plug in my negative 1 for s, I get negative 1. Sorry, move that over a bit. Minus 4 times negative 1. So on this side, I basically got 3. On this side, I got negative 1 plus 4, which is also 3. So that is a true statement. So I know that t equals 0, s equals 1 in both of these equations will give me the point where they intersect. Okay, so I don't have that yet. So I'll come back over here. And I don't have to plug them into both equations. I can just plug them into one now that I know they do have a point of intersection. So for example, I could say x, y, z is equal to, now to get, if I use my t equals 0, I can very easily find this, right? Because all of these terms with t and they all turn into 0 because t is 0. So I know my x, y, z values will be 1, 2, 3 in that order. So that is my point of intersection. Okay, now that was a lot of work to find it. Okay, so what do we have to do now? Remember, we're trying to get the equation of the plane that's defined by these two lines. So remember what we need for the equation of a plane. We need a point that's on the plane. Well, we just found one. Okay, now you might say, well, what about these points? Well, they don't have to be on the line. It is true that that point is shown here, but you can't assume that the position vector defines a point that's on the plane. You only know that it's a point on the line. So you have to do this process anyways. You can't just be second guess and say, well, we could have just looked here. Well, that's not true, okay? Because it could have been an infinite number of points that were on the line that just happened to be the one that was the point of intersection. So in order to find the plane, and I'm going to use my pi to represent the plane, it's going to be r equals, and I've got the point that's on the plane. It's 1, 2, 3. So that position vector gets me to the plane, and then I just use two position vectors, sorry, not position vector, direction vectors that define the plane. Well, I've got these two. Here's a direction vector of the first line, here's a direction vector of the second line. You do a quick little check here, and you can see these are not scalar multiples of each other, so I can use them both. So I'm going to do my scalar variable s times the first direction vector, 2, 3, 4, plus t, my second scalar variable, times the second direction vector of the second line there, 1, 2, negative 4. And there you have your plane. Okay, so a lot of work to find that point of intersection, but that's by far the most amount of work we're going to have to do on this page. So once you've got the point of intersection, and basically that will be the only point that those two lines would have in common. That's the only point that we could actually find right away. Okay, the second case, it says, again, we're trying to find the equation of the plane using 3 non-collinear points. So if you go back to the first page again, that was one of the other 4 types of questions you could get, 3 non-collinear points. Okay, so this one is actually pretty quick. I've got these 3 points. So in terms of position vectors, I've got a choice of 3 position vectors right here, but I do need 2 direction vectors. So here I have to choose, well, I'm going to choose combinations of 2 of the points to create the direction vectors. So this is kind of arbitrary. You could be using different direction vectors. If I chose BC as my first direction vector, so remember how that works, it's going to be 2 minus 0 as my x component, negative 1 minus 1, so that's negative 2, and 0 minus negative 1. So 2, negative 2, 1, that's our first direction vector. Now I have to pick another combination. So I could pick BD or I could pick CD, it doesn't really matter. And I could actually pick something in a different order. It doesn't have to be alphabetical. So I could pick DC. And there is a bit of a strategy to picking the right 2 direction vectors if you're looking for the angle at a certain point. For example, if they then wanted me to use this equation to find the angle at point C for these points, I definitely want to have the direction vectors that both involve C. Okay, now DC, so this time I'm going this way, so it's 2 minus 0. So first component is 2, negative 1 minus 0, and 0 minus 1. Okay, so I've got 2 direction vectors. I've got 3 potential position vectors from the 3 points we know are on the plane, and now I can create my vector equation of this plane. So it's R equals, and whenever I choose, well, which one of these points do I want to use for to create my position vector, I always try to pick the simplest one. So if I have to work with it later, it's nice, easy math. So I'm going to pick 0, 0, 1 as my position vector. And there's nothing wrong with picking the other ones. They're all correct. And now I'm going to add scalar multiples of my 2 direction vectors. So I've got S times the first direction vector, 2, negative 2, 1, plus T times my second direction vector, which is 2, negative 1, negative 1. And there I have my equation of that plane from 3 non-collinear points. So let me back out a little bit. Okay, so that was easy compared to the last one at least. Let's look at the third option here where we have a line and a point that's not on that line. Okay, so go back to our information possibilities. So that was the first one here, a line and a point not on the line. So let's see how we do that. So there's the point. It's got its coordinates there. Here's the line. You can tell it's a line in R3 because it's got 3 components and it's got 1 direction vector. So that's only a line. Okay. So in order to create a plane, I actually have to have two direction vectors. Well, I've got one there. I've also got, I could use this point, or I could use this point as my position vector. Sorry, yeah, position vector. I do need a second direction vector. Second dv. So how do I get that? Well, I just mentioned that I have 2 points that I know that are on the line. Point A and the point that I get to from my position vector. So if I just, I'll call it M. Okay, so I'm basically pretending that's a point. So I've got my point 0, 1, 2. And if I subtract, and again, it doesn't matter which order you subtract, I'm going to subtract in this order. So 1 minus 0 is 1, 2 minus 1 is 1, and -1 minus 2 is -3. So there's a second direction vector. There's my first one, and I guess I'll just keep using, like, it doesn't really matter which of these I use. Maybe I'll change it just to show that you can. So my equation of the plane is r is equal to, and I'll use maybe a new position vector, like I said, just to show we can. It would be totally fine to keep that position vector here, plus scalar multiple of, I guess I'll use my new one to keep that as with the t, s times 1, 1, -3, plus t times the original direction vector of the line, -1, 0, 3. Okay, that wasn't too bad. Okay, so we've looked at 3 of the 4 situations that we could create an equation of a plane. The fourth one, 2 parallel and distinct lines. Well, that is here. So remember, we called them non-coincident lines here. Distinct is the same as non-coincident. Distinct means they're different. Okay, coincident means they're the same. Okay, so now we've called these L3 and L4, I guess because we had L1 and L2 earlier, yeah, in part A. So how are we going to do this? So we've got 2 lines, they're parallel, and they're distinct. So if you look at the direction vectors, you could tell that they're parallel because the direction vectors are scalar multiples of each other. If I multiply this direction vector by -1, I would get that direction vector. So that, in fact, shows you that they're parallel. You'd have to prove that they're distinct by showing that that point 1, 2, 1 is not on this line 4, or that this point 3, 4, 0 is not on the line 3. We don't have to do that. We're just assuming that they are distinct lines, but that's how you would do it. Now, so I can't use both of these direction vectors because they are collinear. They're parallel. They're scalar multiples of each other. So I need a second direction vector. And how do I get that? Well, I happen to know that these 2 equations have given me 2 points that are on the plane, 1, 2, 1, 3, 4, 0. So I can create another direction vector by subtracting those 2 vectors. So if I go subtract them this way, I get 1 minus 3, 2 minus 4, and 1 minus 0. So -2, -2, 1 is my second direction vector. I'll use this one as, well, I'll use it as my first so they don't have the negative signs. You could use that as your first, nothing wrong. And I can use either one of these position vectors because both of those points are on the plane. So here is the equation of the plane pi. R is equal to, I'll use the first position vector 1, 2, 1, plus I'll use the direction vector from that second line, 0, 1, 2, with a scalar multiple of s. And now I'm going to add on my newly created second direction vector with scalar multiple of t, -2, -2, 1. Okay, so there we have our fourth equation of a plane. All four of these part questions had different given information. So it's important to know how to do all four of these because you could be given any one of these types of questions. Okay, let's go on. Example 2. Okay, a plane pi is given by the following vector equation. So this time we've got the equation. We don't have to create it. We want to find 2 points, and I believe that should be plane. Find 2 points on the plane, and then we're going to find a line on the plane, and we'll read that part C later. It's a little more complicated. So if I want to find any 2 points on the plane, if I change my vector equation into parametric equations, I've got x equals -1. If I read across here, -1 plus 0s plus t, so I don't have to put the 0s because it's just 0. Y is equal to, I've got 0 plus 2s plus 0t, so it's just 2s. Sorry, this should be, I wrote down the wrong letter here. X is equal to -1 plus 0s plus 1t. I wrote down s instead. And then z is equal to 2 plus s minus t. Okay, now I can come up with as many points as I want using these parametric equations. And the way I do that, I build a little table to help me. Okay, I'm going to have 5 rows. And I'm going to have, well, if I only want to find 2 points, okay, I'll build like a 3x5 matrix here. So at the top, I'm going to have value of s, value of t, and then values of x, y, and z. So and this is a pretty common way of finding points on planes. You just pick some arbitrary combinations of s and t. So I'm going to pick 1, 1, and I'm going to pick 0, -1. No apparent reason. I like to keep the numbers small just so the math's easier, but those are my 2 combinations. Now what we do is we take these values of s and t and we plug them into, well, x, y, and z to get our x, y, and z values for that combination of s and t. So for example, y is -1 plus t, so that would be -1 plus 1, so that would be 0. Y is equal to 2s, so that would be 2. Z is equal to 2 plus s, so that's 3, minus 1 is 2. Okay. So I just found 1 point. So 2 points on the plane pi. The first point is 0, 2, 2. Okay, if I do the same for this combination of s and t, I've got x equals -1 plus t, so that's -1 plus -1, -2. Y is equal to 2s. Well, s is 0, so y is also 0. And z is equal to 2 plus s, so that's still 2, minus -1, so that would be 3. So my second point is -2, 0, 3. And I've got my 2 points. And you can see I could create as many points as I want. These don't have to be just 0s and 1s. They could be 2s, 3s, and 4s, or 20s, whatever you'd like. So that's how you get points. Use it from a vector equation. You create the parametric equations and then come up with combinations of s and t, or whatever your scalars happen to be for that vector equation. We want to find a line on the plane. So now that I've actually got 3 points on the plane, haven't really talked about it, but that point, there's a point -1, 0, 2 also that I could use, but let's go with the 2 points I just created. I want to find a line on the plane. Well, I've got 2 points on the plane, so let's come up with a equation of a line in R3. So I'm going to have R is equal to, and I can pick. Well, actually, I'll pick the original point there, -1, 0, 2 as my position vector, and then I'm going to create a direction vector. So from here, I'll come up with a direction vector by subtracting the 2 vectors. So if let's see what we can do here. I could, okay, 0 minus -2, that's 0 plus 2, so that's 2, 2 minus 0, and 2 minus 3. So from those 2 points, I have a direction vector, and I can combine that with the position vector to the original point on the plane, and put that scalar multiple in front of this, 2 to -1. Okay, and that's how you get your, and you can tell this is a line because it's got only one scalar with one direction vector. Okay, last question here. Find the vector equation of a line that passes through the origin and is perpendicular to this plane. Okay. Find the vector equation of a line that passes through the origin and is perpendicular to this plane. So, if I go back to the original equation of the plane, I've got my 2 direction vectors that define it. Now, if I want a normal to this plane, basically a direction vector that's perpendicular to both of these, that's basically what I'm looking for. I'm going to do the cross product of those 2. So just a reminder, so this is something I mentioned earlier. Sometimes you need to know how to do cross product to get equations, and this is one of those situations. So the direction vector is found by the cross product of the 2 direction vectors. Okay, so we've got 0, 2, 1. Do a cross product with 1, 0, -1. Guess I don't really need the commas. Okay, and when I do that cross product, I won't go through the calculation, but well, maybe I will. So if I'm doing the first component, I cover up the first column. I get 2 times -1. That's -2 minus 0 because the product is 0. So that is -2. To get the second component, I cover up the middle row. That's going to be 1 times 1 minus 0, so just 1. And to get the third one, I cover up the third row. 0 minus 2 is -2. So this is my normal to the plane that we defined, that was defined at the beginning. Okay, so we're going to use that as our direction vector because the line that we're creating goes through the origin and is perpendicular to the plane. So this is the direction vector of a line perpendicular to a plane. So we're all set there. Now in terms of a point, well, they told us it goes through the origin, so that's our point. Okay, don't forget there's three coordinates because we're in R3. Now I could put, when I'm creating this, I could put position vector 0, 0, 0, but it's really adding no value. It's not going to be used in terms of combining vector combinations of vectors. So I'm just going to leave that out and just stay with the scalar multiple of the normal. So this would be the position vector, but it's not needed in equation. Okay, so this is the equation of the line perpendicular to the plane that goes to the origin. Okay, so that's it for the lesson. Got some homework questions here for you to practice. And the next lesson, the final lesson of the unit, we'll be looking at Cartesian equations of planes. So until then, have a great day.